Chapter 2, Section 2, and I want you all to think about, this is actually on rates of change and limit. So I want you to imagine that we have this cliff. Okay, here's our cliff. And we take a rock, here's a rock, and we're going to drop the rock off the cliff. All right, we drop it so we don't give it a push, it just falls. All right. So we have gravity pulling it down, which is 9.8 meters per second squared. And I'm going to, to make it easy, it's going to disappear for a minute, I'm moving it over. Let's just call it 10 meters per second squared because that's a little easier to work with, right? So the equation for how far the rock has fallen, its distance, I'm going to call it S, okay? S is a distance in meters of how far the rock has fallen, correct? Okay, so I'm going to say S is a function of time. And the equation for how far the rock has fallen, S of t, because S is a function of time, is 1/2 gravity times time squared. And if you have taken physics, this is something that's familiar to you, okay? Gravity has been approximated to be 10 meters per second squared, and I should probably do this. This means approximately. So that means that the equation for the distance of the rock at any given time, of course before it hits the ground, because when it hits the ground it stops moving, we're all here, is 5t squared, approximately. Does that make sense to everyone?
Yes.
Yeah. Okay. So I want to take a look at the travel, how the rock traveled in terms of where it goes. So I'm going to go ahead and open a new page. It's 5t squared. So I'm going to open a page below. And we're going to look at a graph of distance versus time of how the rock traveled. So I'm actually going to do a couple of them. So this is, we'll start with one graph, and then we're going to examine that graph a couple of times. So here's the s-axis, and this is the t-axis, okay? So let's make some tick marks. Remember the function. I'm going to make the function a little smaller. The function is s, my font is too large, let me make it smaller. The function is s equals, the distance is 5t squared. It's a parabola. It's a parabola, it's going to be going up like a cup. Okay, I know the rock is going down, but we're talking about how far the rock traveled, right? So I'm going to have it go up to, say, this is 50 meters. All right? So I'm going to try to subdivide this. Let's see. This would be, well, see if I can do 5 parts. 10, 20, 30, 40, 50, right? Okay. So at time, I'm going to have this go just time 1, time 2, time 3. So we're not on the same scale here. This is 1 second, 2 seconds, 3 seconds. This gravity makes things move pretty quickly, right? Well, my first point is here. At time 0, we've moved 0. At time 1, we've moved 5, right? So that puts us about here. And at time 2, 2 times 2 is 4 times 5 is 20. We're at 20. So that's 10, 20. So we're about here. And then at time 3, 3 times 3 is 9 times 5 is 45. So we're about here. And this is the parabola. You can sort of see how it's curving, right? All right, so let me draw the curve. I'm going to draw the curve in red. Here's the path of the rock. It's parabolic. It's pretty, actually, let me make it a little bit more curved because it's sort of flat down here, really. I don't know if that's any better. The origin is the vertex. Look good? Make sense? Okay. So, so what I want, I'm going to take this and I'm going to go, and I want to take a couple of examinations of this function, all right, as we talk about limits. So I'm grabbing, it's going to disappear for a minute, copy, and I'm going to paste it a bunch of times. So it's coming back. and we're going to look closely at this graph multiple times, and so I want to have multiple graphs to examine what's going on with this, okay? And so maybe this might be more than I need, but better more than not enough, because if I start writing on top of it, I don't want it to be difficult for you to see. So let's look at this first one. Okay, we know that the speed of the rock is the change in distance over change in time, correct? Okay, so I can actually say, let me use a black font here. I can say that, okay, actually it's the speed, right? But it has one direction, right? So I can call it velocity. Velocity is speed with direction, right? So I can say that the velocity, because I can easily say velocity and not speed, it is also the speed, but velocity is speed with direction, and this rock is going in one direction, it's going down, there are no other motion components on it, okay? So it is the change, this is a delta, it means change, the change in distance, s is distance, over the change in time, that's the velocity. And just to remind ourselves, that's a Greek delta, that this little triangle here, it's a delta. Delta S over delta T, and it means change. Probably you've seen this if you're taking physics. That usually is used in physics. Okay. So if I want to know what is the change in distance or the speed from, let's say, on the interval from 0 to 3 seconds, what's my velocity, right? Then what I'm going to do is I'm going to start at time 0. At time 0, it has gone a distance 0. That's this point here. I'll do it and we'll use a different color. I'm going to go with, we'll go with green. Okay, so here's green, time 0. It's gone a distance of 0. At time 3, it's gone a distance of 45, right? And so let's connect these. I'm going to make this thicker. And what I'm talking about here is this line right here. I'm going to continue it on. Okay, this is called a secant line. Let's give it a little arrow. We'll have it continue down here. This is a secant line, and it is the secant line between the points. Let me just bring this. Okay, between the point 0, 0, and this point here, which is the point 345. This is the point. X is 3, Y is 45. And if you remember from geometry, a line that goes through a circle or a curve of a circle goes through it in two places is a secant. So this is a secant line. And the slope of the secant line is the rise over the run, right? Which is the change in distance over the change in time. You with me? And it's pretty easy to see here what the change in distance over the change in time is. And I don't want to run out of room. I'm going to scoot this over just a tiny bit so that I have a little bit more room. Let me grab it. It's going to disappear for a second while I move it, so I have a little bit more room to write. Okay, the formula for the from 0 to 3 for the change in distance over the change of time is S. Let me make that font a little smaller. It's S of 3. Oops, maybe it's too big. It's S of 3 minus S of 0 over 3 minus 0. That makes sense?
That's for the secant line, right?
What?
That's for the secant.
That's the slope of the secant line in the interval from 0 to 3. And so that's because we're trying to find the velocity from 0 to 3. I'll move the 0 to 3 out of the way. We'll put the 0 to 3 up here. We're looking at 0 to 3. And this S of 3 is 45. S of 0 is 0. We've got a time 3 minus time 0. And of course, it's 45 over 3. And this is meters per second, the speed, right? Or velocity, because we know the direction. 3 goes into 4 once with 1 left over. So it looks like 5 meters per second. That's our average velocity. This is an average velocity. Let me highlight this. This is sort of the answer if we were looking for what is the average velocity. There it is. Okay, so I probably should, when we look at velocity here, I'm going to put velocity AVE, velocity average. Okay, let me just take a peek at that. So we found the average velocity, and the average velocity is the slope of the secant line, correct? Okay. So, as a matter of fact, let's write that down. That's important. That the velocity average on an interval from A to B is equal to, let me see, the ratio, well, it's the change in distance over the change in time. And the change in distance for any function f of t, this is just the standard form, is f of b minus f of a over b minus a. Does that make sense to everybody? Okay, so this is the average velocity, and just so that you, when you later you look at this, I'm going to move this down, and I better write out the whole word. Average, so that you know that this is average velocity. We're looking at velocity. Okay, so I'm going to stop here, this video, because I just want you to be able to wrap your mind around this. Is pretty important. That the average velocity for any object, if you have its distance versus time equation, is f of b minus f of a over b minus a. It's in the interval from A to B, that is the time, and f of t would be the function. And the one above, I used s of t. That's just really common in physics, and you'll see it also in calculus, okay? But this is actually not only the average velocity, it's the average rate of change for anything, okay? Yes?
Is S of 3 up there, is that equal to 45?
S of 3 is 45, yeah, because 3 squared is 9, 9 times 5 is 45, right? That would be the height of the function, okay? Let me just stop here, okay? And